Alright, we'll continue with induction motor, the topic 4. Now, just now we actually have run through all the basic of the induction motor. If you recall, how to calculate synchronous speed, ns equal to 1 to F over P, how to calculate slip, which is ns minus nr over ns, and also how to find rotor speed, nr equal to 1 minus s multiply ns, and how to find the rotor frequency is s times f. So that was the part 1. Then part 2, we have to find the rotor current. Remember I said you must visualize a circuit, a simple series circuit or single phase circuit. Rotor current is equal to Ohm's law, ER divided by the impedance, and use Pythagoras theorem to find the impedance. And then we move on to the two conditions for the two different torque. One was the maximum torque when it's running. The slip must be equal to R2 over X2, and the condition for maximum starting torque, right? And R2 must be equal to X2, right? So with that, now let's carry on with the efficiency, how to measure the efficiency of the induction motor and the power flow, as well as the type of losses. Now, efficiency of a induction motor or DC motor or even transformer is always the same formula: output divided by input multiply 100%. Yeah, so that is efficiency. Okay. Now, then move on. We are now in three-phase topic. This is a three-phase AC topic. Now, the input power, when we supply a three-phase input power, how do we get the input power? It's square root 3 VL IL cosine theta. Cosine theta is the power factor. Okay, line voltage and line current. Now, some of you may be wondering how this formula comes about. If you are interested to know, it is actually can be derived from here, right? Now, the three-phase input power is equal to 3 times of the phase power. Yes or no? Right? If you know the phase power, you multiply by 3, right? Now, if it is a star circuit, you will say it's equal to VL divided by square root 3 times I phase cosine theta. Yes or no? VI cosine theta? Phase voltage, phase current cosine theta. 3 divided by square root 3 will give you square root 3. So that will be VL IL cosine theta. Because phase current is the same as line current for star connected circuit. Remember star connected circuit, right? If it is a delta circuit, again it's still the same, 3 times of the phase power, right? And you say 3. Now for star circuit, the line voltage and the phase voltage is the same. So you will say it's equal to 3 VPH multiply IPH. Phase current would be equal to line current divided by square root 3 cosine theta. For star circuit, phase voltage and line voltage is the same. Yeah? Line voltage and phase voltage is the same. So if I put phase, I'll put line is the same thing. So again, 3 divided by square root 3, you get 3 multiply VL IL cosine theta. Okay, and that's how this formula comes about. It is just the proving. Be it a star circuit or delta circuit, the total input power is equal to square root 3 VL IL cosine theta. Right, next. Input power. Okay, then if you still recall, in our DC motor we learned about this. Power is equal to 2 pi n multiply over 60 times torque. Remember this formula in DC motor, right? And in DC motor, I often express it the other way around. Yeah? So we express it as output torque is equal to 60 over 2 pi n multiply output power. Yeah? Or develop torque, then you use develop power. Output torque, you use output power. And what is N? N is the speed. Yeah? N is the speed. Okay, so this is kind of revision material. Efficiency is output divided by input. Input is equal to square root 3 VL IL cosine theta. Y, 3 phase. Torque is equal to 60 over 2 pi n multiply the power. Okay, Right, so now let's move on to the power flow diagram. Now the power flow diagram looks like this. Okay, it's a flow chart. Okay, now this is the input power, and the input power actually goes to the stator, because if you recall the construction of an induction motor, you have 3-phase AC, right? That goes into the circuit. That's your stator, and then it interacts with the rotor. Remember the moving magnetic flux interact with the rotor, and voltage is induced in the rotor. So current carrying conductor in the rotor react with the magnetic flux and makes the motor move. So the first power, the input power is actually to your stator, Okay, and what is the formula for input power? That is equal to square root 3 PL IL cosine theta. Right? Now, this is stator. So there are losses that happens in the stator, right? In terms of heat loss, eddy current loss, and so on and so forth. And this we call it a stator loss. So taking the input power minus the stator loss, the energy, the power left behind will go to the rotor. So that we call it the rotor input power. Right? So it's about transferring of energy. Input power go to the stator, take away the losses, the rest is transferred to the rotor. And again, the rotor would have losses. You would have your rotor copper loss, your rotor iron loss. Alright? But the more important loss in the rotor is the copper loss because of wire. So we say the loss here is called the rotor copper loss. Cu stands for copper. So the rest energy comes into the stator. After the losses, go to the rotor. Rotor after the losses becomes the developed power. In our DC motor, we call it developed power. But induction motor, we call it gross mechanical power. Okay, gross mechanical power. PM. Okay, gross mechanical power. Then you have the rotational loss. Okay, rotational loss, which means the friction, the vibration, the heat loss. So that's all rotational. Then gross mechanical power take away the rotational loss, then become the useful power, which is called the output power. Right? So this is called the power flow diagram. You must remember the diagram, because otherwise you cannot solve the power flow related questions in the tutorial. Okay? Right, let's try again to see whether we can remember them. Not only that you must know the power flow diagram, you must know the so-called the name of the power. Otherwise, you cannot map them into the power flow to get problem solved. Okay, start off. The power goes to the stator. This is called the input power, right? Which is square root 3 PL IL cosine theta. And the losses is the stator loss. Then the rest go into your rotor input power. And rotor also would have loss. The major loss is called the copper loss. Then the balance go to the gross mechanical power. And gross mechanical power would have this miscellaneous loss, which is the rotational loss. Then becomes the useful power, which is called the output power. Alright? So now if you know the power flow diagram, let's put numbers. If I say this is equal to 1600 watt, and this one is equal to 40 watt. How many watt is here? 1600 minus 40, that will become 1560 watt. Right? And if I say this is 60 watt, 1560 minus 60 become 1500 watt. Right? And if the rotational loss is equal to 20 watt, 1500 minus 20 become 1480 watt. Get it? 1600 minus 40, 1560. 1560 minus 60, 150. 1500 minus 20, 1480. Or 1600 minus 1560 equal to 40. 1560 minus 1500, 60. 1500 minus 1480 is equal to 20. Or if you go backwards, 1480 plus 20 is 150. 150 plus 60 is 1560. 1560 plus 40 is 160. Alright, so be flexible with your flowchart. Put in the numbers, then the rest will become, you are able to find out what are the values. And that's called the power flow diagram. Okay, so that was the power flow diagram. Right, the next thing is about three formulas about the power flow diagram. If I were to tell you that rotor copper loss is equal to S multiply rotor input. That means, remember, slip is percentage, right? Slip is the percentage, right? So if I say the rotor copper loss is 4% of this is 4%. If this is 4%, how much is here? Of course, it's 96%, right? 4 and 96, 100%. Yes? So if rotor copper loss is equal to 4% of rotor input, then the gross mechanical power is equal to 1 minus S times rotor input. Yeah? If it is 4%, here is your 96%. Now, these formulas are provided in the exam. And for induction motor, in fact, I think this will be the only two formulas given. Now, if you use this formula, this divided by this, right? P rotor copper divided by gross mechanical power. So you have S times rotor input divided by 1 minus S times rotor input. Correct? This equation divided by that equation, you cancel this one off, right? So the equation becomes rotor copper loss divided by gross mechanical power equal to S1 minus S. Right? So these are the three formulas in the power flow diagram. And they are given in the exam. They are given in the exam. You must know how to use it. Now, when do you use it? Just now, remember when I give you numbers. If it's just based on flowchart, this minus this equal to this minus this equal to this minus this equal to this, you get the answer. Then don't have to use this formula. When you get stuck, you get missing information, then you cannot do the normal way of counting, then you have to use the formula. Right? I give you an example. Say for example, I know this value, right? I know this value, and I know slit, and I know slip. Okay? Then you are asked, find me the gross mechanical power. Okay? Find me the gross mechanical power. Right? Then what do? You know this, you do not know anything else, but you're asked to find this. Then no choice but to come to the formula, right? Because you know slip, and then you know rotor input, then you can find gross mechanical power. When the normal way of power flow chart doesn't work, that's the time you turn to the formula. Okay? So that is called power flow diagram. Efficiency and the type of losses. Okay, let's come back, do it one more round before we go to do some examples. Power flow diagram. Input power. Input power is to stator. And then it's equal to square root 3 VL IL cosine theta. The first loss is from the stator loss, which actually just like transformer is iron loss and copper loss. Right. Then the rest go to the rotor. We call it the rotor input power. And then rotor loss. Now also got iron loss and copper loss, but copper loss is the majority. It's the main one, so we just say rotor copper loss. Estimated. And this is the gross mechanical power, which is equivalent to the developed power in the DC motor. And this is the rotational loss. Yeah? And then the output power. Okay? Remember, you can do your mathematics in a very logical manner. Okay? Say for example, if you know that this is equal to 20 kilowatt, and then here is equal to 22 point, meaningful numbers, right? 20.4 kilowatt. Then do you know what's the rotational loss? Of course, it's 0.4 kilowatt, right? And then if I say here is equal to 20 21 kilowatt. If I say here is 21 kilowatt, do you know how much is this? 21 minus 20.4, so it's 0.6 kilowatt. Right? And if I say here is equal to 21.5 kilowatt. If this 21.5, here is 21, how much is here? 0.5 kilowatt. So work on the logical manner. Either you work this way or you work that way. Yeah? And it fails, if it fails, then turn to the formulas. Alright, let's try questions on power flow diagram. Again, I'm referring to the tutorial questions. Okay. There's this tutorial question. It says, example, the power input of this three-phase induction motor is equal to 40 kilowatt. Right? It is a 500 volt induction motor. It's 6 pole. It's 50 hertz. Okay, and the stator loss is equal to 1 kilowatt, and the friction and windage loss is equal to 2 kilowatt. Now, another word for rotational loss is actually called friction and windage loss. It means the same thing, right? When you see this word, it means rotational loss. Okay? Alright. Okay, so this is the question, information given in the question. So if I were to map onto my power flow diagram, 40 kilowatt is here. Okay? And stator loss is here, 1 kilowatt. Okay? Rotational loss is 2 kilowatt. Straight away, I know that 40 minus 1 will give me 39 kilowatt. Yes or no? Alright? Okay, let's try. Part A. What is the rotor input power? Of course, the answer is 39 kilowatt. Yeah? 40K minus 1K is 39K. Part B. What is the slip? What's the slip? Can you recall what's the formula for slip? Slip is equal to Ns minus Nr divided by Ns. Right? And do I have information to find the slip? Yes, I forgot to give you one information. You're told that it runs at 975 RPM. So, what is Ns? Ns 120 F over P. What's Nr? 975. Do I know F? Yes, 50 Hertz. Do I know P? I'm told that it is equal to 6 pole. Right? So slip can be found. Right? Then the question carry on after finding the slip. It says find the rotor copper loss. Right? Now you have this information. You ask for this. You do not know this. So there's no choice but to make use of the formula. Can we still recall what's the formula? The formula is P rotor copper loss is S multiplied P rotor input. Slip I've calculated, rotor input I know, so the answer is found. Rotor copper loss is found. Part C. Find the gross mechanical power. Okay, gross mechanical power. If you refer to the power flow diagram, rotor copper loss you already found. You have this, you have this. Can you find this? Of course. This minus this will give you this. Right? Or another way to use the formula, this is equal to 1 minus S multiplied that. Right? So gross mechanical power is either equal to P rotor input minus P rotor copper loss, which you have the information you can find. Or you prefer to use formula 1 minus S multiplied P rotor input. Also can. Right? So that's part C. Alright, part D. Part D say find the shaft power. Now shaft power means output power. Right? So now we already found gross mechanical power. We know rotational power. Am I able to find output power? Yes, the answer is equal to Pm minus P rotational loss. And I get the two values. So shaft power can be found. Then I'm asked to find the shaft torque. Shaft torque is equal to output torque. Alright, and what is the formula? 60 divided by 2 pi n multiply the output power. Yeah? Because output torque means output power. What's n? N is the speed, 975. Yeah? So I have these, so torque can be found. So that's part D. Last one, the efficiency. The efficiency. Efficiency is equal to output divided by input multiply 100%. Yeah, where's the output? You already found the output power, right? So it's this value. Input, that's the initial value. So plug the two values, your answer is out. Okay, so that is the power flow diagram. Okay, I think with more practice in the tutorial, you should have no problem. Just remember, power flow diagram, you must know it by heart, otherwise you cannot trace what is what. First thing goes to the stator, then go to the rotor. Right? Maybe now it comes to a good juncture for me to explain to you why is it that in the rotor current we say R2 and X2. Remember the standstill resistance? Because we actually take it as a model of a transformer model. So this is the stator and this is the rotor. Okay, and then you have your three-phase power supply coming in here. Remember, voltage is induced here. So if you take it as a transformer model, this is your primary circuit, and this is the secondary circuit. And if you recall in our transformer circuit, this is the primary, this is the secondary, right? Primary circuit and the secondary circuit. Yeah. So the primary circuit, you have your R1, X1, and secondary circuit you have R2 and you have your X2. And then when we were doing the per phase rotor equivalent circuit at the beginning, we are referring to the secondary circuit or primary circuit. Of course, it's secondary circuit. That's why we have the R2 and X2. Remember the standstill resistance and standstill reactance? Yes. So now is a good time to explain to you why in our equivalent circuit, our per phase rotor equivalent circuit, we call it R2 and X2 instead of call it R1 and X1. Okay, that is all for the efficiency part.